Hello everyone, my name is Karim Ali and I'd like to talk to you today about a study of call graph construction for JVM hosted languages that we published last year at TSE, and we have a chance now to present it as a journal first paper at FSE. This work is joint work with Xiaoyi Liu, Chauni Lai, Andrei Lotek, Julian Dolby and Frank Tipp. So we all know that Java has been one of the most prominent languages with all the runtime environment that comes along with it, with all the tools that come with it, with all the compilers and just-in-time compilers that come with it as well. But nowadays, Java is not the only language that compiles with the JVM. There is a whole bunch of other languages that also compile and target the JVM as a runtime environment, like Scala, OCaml, Groovy, Clojure, Python, JRuby or Ruby, and so on and so forth. The thing about that is, while we have all these languages that target the JVM, we have all those static analysis tools and static analysis frameworks like Wala, Dup, Soot, Chord, and so on and so forth that target analyzing the JVM bytecodes. And the promise there is that if the analysis framework is capable of consuming JVM bytecodes as input, then we can just analyze any kind of JVM bytecode. And this is exactly the question that we wanted to answer in our study. Can we possibly analyze any language that compiles the JVM bytecode just by using the existing static analysis infrastructure that we have there? So that is really our problem statement. So we can produce all the JVM bytecodes from programs written in many languages other than Java. Can we use those static analysis frameworks to analyze those bytecodes? And as a vehicle for static analysis, we focused on call graph construction as a representative problem because it is really going to be necessary in any kind of inter-procedural analysis, taint analysis, data flow analysis, pointer analysis, and so on and so forth. So it is a good starting point as from an analysis perspective in the study that we conducted. So we primarily focused on the most commonly available languages at the time where we conducted our study: Scala, OCaml, Ruby, Groovy, Python, Clojure, and Kawa, which is a flavor of Scheme. To conduct our study, or before I go deeper into the actual study and how we conducted it, I'd like to go briefly over some of the JVM features that were particularly interesting to explore in our study. The first is method handles and the second is invoke dynamic. So both of these in method handles and invoke dynamic, they were introduced back in Java 7 and Java 8 to support JVM-based implementations of dynamic languages. And the premise there was that it is going to be more efficient than traditional reflection. Nowadays, these features are actually used by Java itself to compile features like Java 8 closures, which typically translate into invoke dynamic instructions, and also used in other languages, as we're going to see in our talk later on. So the adoption of these JVM features, method handles since Java 7 have been used in OCaml to implement some of the dynamic language features there. And in Ruby and Groovy, they have a flavor of, if you compile the language to JVM bytecode, you can tell the compiler that you want to use invoke dynamic to implement certain features of the dynamic languages. So these features have been seen or have seen adoption beyond Java 8 or Java itself. Scala also is one of the other languages that also use invoke dynamic to implement closures and to implement trait mixins and so on and so forth, as we're going to see later in our course, later in our talk. So the approach that we followed for our study follows both a qualitative approach and a quantitative approach. In the qualitative approach, we focused on compiling small programs, hello world programs really, to bytecode to understand what goes into the compiler and what will come out of it for these simple programs. So it gave us more of an in-depth analysis into these small programs because we crafted them by hand. We identified challenges to static analysis based on our observations flowing from this qualitative study. In the quantitative study, we got 10 programs that were implemented in all 7 languages under study from the Computer Language Benchmark Game Suite. And for each one of those programs, we construct static call graphs using the standard 0CFA data flow-based or propagation-based analysis in Wala, the analysis framework, And we also construct dynamic call graphs using WALA runtime instrumentation call graph generation. We compare for each program, for each run, we compare the call graphs with respect to imprecision and unsoundness to get more insight into what affects the implementation or which language features affect the soundness and imprecision of the generated call graphs. We also study those correlations between performance, runtime performance, and also imprecision and unsoundness, and how amenable the JVM bytecodes generated by certain language compiler is to static analysis and how that relates to performance. So for the qualitative study, we found that for all the dynamic languages, Python, Ruby, Clojure, and Groovy, they typically follow the same kind of compilation technique or compilation approach. So what happens there is one call typically generates, one call in the source language typically generates a chain of calls that goes into the language runtime libraries and comes back to the application code. So it's a very complex chain of calls that may induce a lot of imprecision and maybe even sometimes unsoundness in the generated JVM bytecode. To do any kind of precise static analysis, including call graph construction for any of these four languages, you need at least context-sensitive analysis that can differentiate between call sites, different call sites in the program to the same method to the same target method that it may dispatch to at runtime. Without context sensitivity, there is no hope in getting any kind of meaningful or useful call graph that could be then used in other analyses or other client analyses as well. Most static analyses that on these four languages, specifically call graphs, will be unsound due to the following reasons. There is a lot of use of reflection, for example, in module imports in Python. There is a lot of use of runtime code generation. There's just no way to reason about it at static time or at compile time. For example, in Ruby, you have that as well to implement certain dynamic language features. And there is also use of mutable call sites in both Ruby and Groovy, where you cannot reason using invoke dynamic and method handle even in the currently existing static analysis infrastructure, which has been developed after we conducted our study, that doesn't really support mutable call sites, because these call sites are capable of changing their target method at runtime without having any prior knowledge at static time or compile time about these call sites. For the other more statically typed languages, like Kawa, for example, this is a Hello World program. We see a different approach there in the compilation technique that yields a different result. So there is no use of reflection in the Hello World program whatsoever. There is also no unsoundness that we observed in the generated call graph. So any potential runtime behavior of a program is exhibited in the static call graph. OCaml is very similar to Kawa. So there we also we have seen direct function calls being translated using invoke static, which is perfect because then we know for sure what is the target of that method call at static time. We don't even need to do any method resolution or dynamic dispatch to model it. First class functions are represented using method handles, which is also great because now static analysis tools have the capability to understand or to reason about method handles. So that is also a plus for precise and sound static analysis for OCaml generated bytecodes. There's also no use of reflection or even invoke dynamic in the generated bytecode, which makes bytecodes generated for this Hello World example by OCaml more amenable to static analysis and call graph in particular than other languages as well. For Scala, it's probably the language that has generates bytecodes that are the most amenable to static analysis compared to the Java bytecodes or the bytecodes generated by the Java compiler. Closures in the Scala language are translated into anonymous classes, typical anonymous classes in Java, with an apply method that implements the body of the closure itself. The Scala compiler also introduces some reflection, again at the time of the writing of this paper, for structural types and to implement their features. So this is about what we found from the qualitative study, but we wanted to do a larger case study with more programs and more across all the languages to understand the effects on a larger scale. So we conducted a quantitative study, as I said, with 10 programs from the Computing Language Benchmark suite, and the experimental setup is basically the following. So we made sure that we use workloads for these programs that guarantees a basic block coverage that is roughly 87% across all the benchmarks. So we exhibit most of the runtime behavior of the programs in the dynamic call graphs that we generate. There is no library code instrumentation, as in the language runtime, as in the library dependencies of the programs, because that yielded a very, very slow instrumentation process that made it prohibitive for us to conduct the experiments that we wanted to conduct over all these languages. We also had to make sure that we consistently handle JVM bytecodes that are related to finalize methods and static initializers, such that they are consistent across all the language implementations, and that took a significant amount of engineering effort in collaboration with the Wala developers, such that we can ensure this consistent behavior across all the language implementations. So I'm not going to even go into the dynamic languages, because it was really a hopeless case to conduct any kind of not really to conduct any kind of qualitative analysis, but to really get any useful results. It was basically all the call graphs are unsound. There is a lot of imprecision. Most of the behavior of the runtime program is not exhibited in the static call graphs because of how much reflection, how much runtime code generation is being used there. So it wasn't really that much different than the Hello World examples that we found. But for some of the languages that I'm going to discuss here, we found actually very surprising results and very interesting results that I would like to share with you. So for Kawa, for example, for Scheme, which is an implementation of Scheme, similar to the Hello World example, we didn't observe any unsoundness in the generated call graphs, meaning all the nodes, all the edges in the static call graphs, in the dynamic call graphs were there in the static call graphs. We also observed a lot of imprecision, so the static call graphs were significantly larger than the dynamic call graphs, which we attribute to having a lot of dynamic dispatch, a lot of virtual dispatch, and a lot of method resolution that we had to that was imprecise to reason about without too much depth in the context-sensitive analysis that we were running. For OCaml, we found about 5% or even less than 5% of unsound edges due to a specific use of reflection in Java Lang Reflect proxy to implement certain dynamic features in the OCaml language. But it was really negligible unsoundness compared to some of the other dynamic languages where most of the call graph was not even there. You would just find a call from the main entry point of the program to maybe one runtime library, and that's it, and you can't find any other edges there. We also found that the static call graphs are significantly imprecise compared to the dynamic call graphs due to similar reasons as in the Kawa language. For Scala, the situation was a little bit different than OCaml. Again, similar to Kawa, we couldn't find observe any unsoundness in the programs that we found. So all the runtime dynamic call graphs were exhibited in the static call graphs. The static call graphs are not that imprecise compared to the dynamic ones. So the situation for Scala was much better than the situation for Kawa and for OCaml as well. Using an optimize option in the Scala compiler, which optimizes the bytecode a little bit, wasn't useful in the sense that it didn't really affect the results of our experiments that much, and it didn't really cause any significant changes or differences for both soundness and for precision in the generated call graphs. The other thing that we also did is that it wasn't enough to just look at the computer language benchmark programs. So for each one of those languages, except for Ruby, we got two large applications, one of the commonly available applications that are open source on GitHub for each one of those languages, and conducted the same experiment with them. So the same experiment, the qualitative study on each one of those languages, and figure out what is the static call graph, what is the dynamic call graph, and that was also a significant engineering effort. But the observations that we got out of that experiment only confirmed the observations that we found from the computer language benchmark suite, which means that even with a larger scale code base or the larger code bases, we could still see the same observations. We could still see the same results that we found on the smaller programs for all these languages. The second thing that we found, or the second thing that we did, was performance comparisons. And for these performance comparisons, we used the Java Micro Benchmarking Harness version 1.12. And we did for each program, for each language, we did 30 warm-up iterations and 30 measurement iterations, where in those warm-up iterations, we ensure that the Java runtime eliminate any kind of noise in the measurements and that the JVM would reach a steady state so that our performance measurements would be accurate enough. And the results that I'm going to share are based on the 30 measurement iterations that happened after those warm-up iterations. We evaluated two metrics, running time and memory usage rate. So in this diagram here, I'm showing on the x-axis all the languages that we had. Each point above each of those languages represent one of the benchmarks from the 10 benchmarks that we found, that we were discussing. On the y-axis, I'm showing the normalized program running time with respect to, or normalized to, the Java runtime. So Java is our baseline here. So 1 means Java, above 1 means slower, below 1 means faster. So across all the benchmarks, we found that Scala programs on average are 1.54 times faster than Java, which is a bit surprising. But on the other hand, it uses 1.7 more memory compared to Java. Kawa has kind of a similar performance to Java, but on the other hand, uses 4.3 times more memory to be able to achieve that. Clojure, even though it's a dynamic language, is a bit faster than OCaml, but uses almost double the memory compared to OCaml to achieve that result. And the last observation that I would like to share with you is, for all the dynamic languages, they are orders of magnitude slower than the Java and also other languages, and they are also using much significant, in the orders of magnitude, larger with respect to memory consumption as well. So not only do you have worse runtime performance, but you also are consuming much more memory to achieve that worse runtime performance. So some of the lessons that we have learned along the way are not all JVM bytecodes are created equal. You cannot assume that if your static analysis tool supports analyzing JVM bytecodes, that you're going to be able to analyze any bytecode that is generated from any language compiler. String-based compilation techniques that many of those dynamic languages use severely hinder static analysis, and we have seen that with the smaller examples and with the larger programs and larger applications as well. Finally, dynamic languages may still be compiled into analyzable bytecodes, and we have seen that both in Kawa, which is an implementation of Scheme, in certain language features in OCaml, and also in certain language features of Scala. So let me quickly wrap up what I have been talking about in this talk. So first of all, many languages, not just Java, compiled with a JVM runtime, like Scala, OCaml, Ruby, and Groovy. We also have many static analysis frameworks that consume Java bytecodes or JVM bytecodes as input, and the question that we wanted to answer throughout our study is, can we reuse that analysis infrastructure to analyze bytecodes that are compiled, JVM bytecodes that are compiled from compilers other than the Java compiler or not? To answer this question, we followed two approaches, a qualitative approach and a quantitative approach. Qualitative approach with Hello World-like programs, quantitative study that we conducted. We used 10 programs for each language from the Computing Language Benchmark Suite. We also had 2 large programs for each language as well, where we compared the static call graph to the dynamic call graph to see the differences between them. From our experiments and from our studies, some of the lessons that we learned that I've shared with you, I've shared some of the lessons that we have learned as well throughout the way. And with that, I'd like to end my talk about our study of call graph construction for JVM hosted languages. If you have any questions, please feel free to reach out to me via email or Twitter, and I will be more than happy to answer any questions that you have, or of course during our session at FSE 2020. Thank you very much. You have a nice day. Thanks for watching.